Hello, everyone. Welcome to yours and my favorite part of the week. That's right, it is your online health psychology course, and I'm here to walk you through the hottest topics in nervous, endocrine, and immune systems and principles of homeostasis. All right, so we got a lot here. A lot of this is kind of going to be a little like listy. So it's like this part of the brain does this, and this is what this does. So that obviously is going to be a kind of by default kind of a feature of this chapter. But we're also going to talk about how and why different systems, immune, endocrine, nervous system, impact health outcomes, and kind of the same idea with homeostasis. Obviously, thus, there's going to be a bunch of like neuro autonomy, different regions of the brain, etc. I'm not really looking for you to memorize kind of like all these specific brain regions. So throughout this lecture, I'll point out things that I really don't want you to focus on memorizing, instead kind of think through these broader concepts. So we are going to talk about, again, specific neuroanatomy and kind of the biological processes. I want you to know some parts of it, but I'll try and flag things that I'm not super concerned about. All right, so with all that said, let's jump into it. We have our outline here, which we don't need to go through. We love to see it. All right, now moving to our global biological systems. Three biological systems of relevance to health psychology are the nervous system, the endocrine system, and the immune system. Systems activate and deactivate tissues, organs, and muscles to control and regulate the body, the emotions, and the mind. There's a continuous interaction via electrical and chemical signals throughout the brain and the body, I should say. The principal objective of the three systems is to preserve homeostasis. And this is kind of a rough schematic here where we have the brain, the immune system, the endocrine system interacting with each other. We got the nervous system in between. And then we got this process of homeostasis, which we alluded to a little bit in the previous chapter, but we'll expand on. So all of these kind of biological systems, these networks that are quite complex, interacting with each other. And it's important to keep in mind that although we will identify particular brain regions associated with particular behaviors, or theoretical, that's actually not that straightforward, it's important not to conclude or overinterpret these results to say X region of the brain causes a behavior. Rather, it could just be a biological process underlying that behavior. For kind of a quick example, just as like you get a little like nervous or stressed out, you start sweating. You wouldn't say that sweating causes stress necessarily, but rather it's kind of the biological process associated with stress, how our body processes stress. And this can be a little tricky with people. There's all kinds of research that suggests that just showing a brain to people will make participants more likely to believe the stated kind of whatever it is the argument is. So if you just put like some neuro kind of stuff next to it, people will say, oh, that's kind of more valid. But kind of neuro research is far more complicated than that. It's really not a one-to-one like, okay, we've identified this part of the brain and it causes X, Y, Z. No, not at all. As we discussed in the previous chapter, and we'll discuss in later chapters, kind of challenges with health psychology, there are also these kind of same challenges with neuroscience, and neuroimaging and genetic research as a whole. So it's important to keep in mind that this is not these are not like that causal situation, but rather kind of think it through as kind of a biological networks which are correlated with kind of these particular behaviors. All right, moving on to cells. We have about 37.2 trillion cells, plus or minus around 0.81 trillion. So basically, this number is effectively meaningless. There's so many cells that it is difficult to even wrap your head around it. There are hundreds of different cell types. The cells in one body have identical DNA, but carry out a coordinated myriad of functions to enable the maintenance of a near stable internal environment. Only by communicating with one another can the necessary high-level coordination be possible. So we have a lot of cells, you may have heard, and there are a lot of connections between those cells. So that cell number, take that and times it by many, and that is basically the amount of neural connections, just the neural connections in the body. So trying to make sense of all that is very obviously very difficult. I once had a professor who held up a piece of paper and folded just kind of like the corner of the page, and the professor stated, this is basically what we know about the brain. So again, quite difficult. But the important part is that these cells are coordinated in complex ways, and they underlie behavior, and especially complex behavior. Moving on to neurons and microglia cells. The two main cell types in the nervous systems are neurons and glial cells. Both are necessary for neurological health. Glial cells provide support and nutrition, maintain local homeostasis, produce myelin, and participate in signal transmission. About 10 to 15% of all cells found within the brain. Multiple sclerosis occurs when an abnormal immune system response produces chronic inflammation, which damages or destroys myelin. So glial cells are often slept on, but there's approximately equal glial cells as there are neurons. So it's kind of they must be doing something. And you can kind of just broadly think of these as our community helpers. They are, again, supporting our neurons, trying to maintain homeostasis. They are providing nutritional supports. They're involved in myelin production. And as you can see on the the figure on the right, you can see a person who does not have a multiple sclerosis on the left-hand side. You can see, so that's one neuron. And on the right side, you can see damage associated, someone with multiple sclerosis, and you can see damage to their myelin. And, so it's kind of eaten and corrosive on the myelin, which kind of makes it difficult for neurons to communicate, and thus that irregular communication is associated with behaviors or symptoms associated with multiple sclerosis. So things such as speaking problems or maintaining a balance, falling down, stuff like that, kind of thought to be associated with this damaged myelin sheet, thus kind of interrupting communication between neurons. And we're not going to spend long on the schematic here, but this is just kind of a schematic of a neuron in a synapse. Well, you don't need to know kind of the specifics about really any of this. It's just nice to look at. Nice to look at. It's quite. I think the colors are quite vivid. Now, why that myelin sheet is also important is because it allows for kind of quicker communication between neurons. Thus, when we, as we grow older, we kind of developed more myelin sheath, which allows us, or kind of the neurological process underlying that kind of increased ability to engage in complex behaviors. So maybe not just physical behaviors, but complex ways of thinking or solving hard problems like math problems and stuff like that. Microglial cells are highly plastic and act as macrophage, that is big eater cells, the main form of active immune defense in the central nervous system. They engage in constant system of microglia. Surveillance protects the brain against any micro-invaders, demyelination, trauma, and cancerous or defective cells. I hope the person who's in that ambulance does not have issues with their microglia. Neurons provide the main wiring of the nervous system as communication devices which connect with each other. So you can see here, this is kind of a specific or larger subtype of glial cells here. Again, you can see that support role. So in this case here, monitoring against any potential disease kind of prevention, stuff like that. Trying to prevent, again, demyelination, so aka the loss of myelination, and damaged cells, stuff like that. Next, we have a schematic here of synapses and neurotransmitters. I'm not going to walk through action potentials because you're going to do that in other classes. I will include, however, a video of me explaining kind of action potentials if you're interested in that. But I will not be going into, will not be reviewing that in this lecture, and thus it will not be quizzed on. However, we'll talk about some broad overviews of it. Synapses and neurotransmission. One major form of communication in the nervous system uses neurotransmitters, which are released across an intercell channel called a synapse or synaptic cleft. Always annoying that people use those interchangeably. This is a chemical form of communication between neurons. At least 60 different kinds of neurotransmitters, and they include serotonin, histamine, and catecholamines. So there's a whole bunch here. And kind of our main idea here is that neurons communicate with each other chemically by releasing these neurotransmitters. These neurotransmitters will alert other connected neurons. So neuron A releases a neurotransmitter, neuron B recognizes it, and then this starts a kind of activation process wherein multiple neurons communicate with each other, and which again kind of underline complex behavior or kind of just unconscious behavior like breathing and stuff like that. Now let's walk through an organization of this nervous system. The command and control center at the top of the nervous system is the central nervous system, the CNS, consisting of the brain and the spinal cord. Decisions made in the central nervous system are communicated via the peripheral nervous system, the cranial and spinal nerves, to the motor effector division of the nervous system. So you can almost imagine like a command and control center. Not exactly, because there's going to be bidirectional, aka the nervous system is going to be affected by other parts, or I should say the central nervous system will be affected by other parts of the brain. But the nervous system also is kind of doing commanding, making commands. And the central nervous system, again, is the brain and the spinal cord, kind of what we think of, as like, the major biological process or neurological processes underlying behaviors. And those decisions made by the central nervous system, again, kind of just your brain, is communicated through various network subsystems of the nervous system, again, such as the peripheral nervous system. And kind of our big kind of takeaway here is that communication from the central nervous system down to other parts of the nervous system. This is called effector division. So what I think of this as is get the F out of here. So it's kind of like it's the central nervous system pushing commands to the rest of your nervous system. So thus get the F out of here. So I'm sending commands outward. All right. So make sure you know the difference between effector division, what the difference is between effector division and the afferent division. The afferent division is communication back to the central nervous system, conducted by the sensory division. So again, we have this bidirectional approach. We have our brain and spinal cord sending down commands to different parts of our body, our motor system, for example, but we also have information feeding back to our central nervous system. So for example, I touch something and I'm like, oh, that's hot. Well, that hot signal is, going from my touch receptors in my finger, working their way up to my central nervous system. So, and it's also, for example, I'm touching things, I'm moving around, I'm like in real time, kind of in a bidirectional, continuous bidirectional process, where the central nervous system, again, is sending out commands, sending out information, get the F out of here, efferent, and other parts of the nervous system, aka not the central nervous system, are sending information back to the central nervous system. That is called the afferent division. Now, there are two branches of the efferent division, again, sending commands from the central nervous down, so get the F out of here. We have the anatomic nervous system, the ANS, which deals with the cardiac muscles, smooth muscles, and glands, and the somatic nervous system, which deals with skeletal muscular actions such as speech and behavior. So my central nervous system is saying, hey, go punch that guy in the face. So it's saying, which will go down the efferent division, because we get the F out of here. We're going from the central nervous system down to our somatic nervous system, which controls muscular actions. And what do? I'm now punching. All right. So that's so we have those two branches of the efferent division. Again, the ANS kind of dealing with cardiac muscles, smooth muscles and glands, and the somatic nervous system dealing with skeletal muscle actions, aka speech and behavior. Make sure you know that kind of broad overview of efferent versus afferent. Okay, so get the F out versus receiving information. I can't really think of an afferent one, the one that starts with an A off the top of my head. All right, working through the nervous system, beginning with the brain. The cortex controls information input, synthesis and comparison, and output and action. These are kind of very, very complex things, and the cortex is a very broad kind of statement, but this is thought to be, very, again, complex behavior, weighing information that it receives, sending out information. So information input comes through receptors that are sensitive either to variations in the outside world or to variations within the body, such as changes in body position. So again, I'm moving around in the real world. I'm sensing things, my sensors, I smell things, I see things, I hear things, whatever. I'm touching stuff, it's too hot, whatever. That information is being communicated to our central nervous system and our cortex. But we're also receiving information from inside our body. So maybe some particular hormone is too much, maybe our body temperature is too high, something along those lines. And that could be communicated back to the central nervous system. So, for example, I'm too cold. I'm like, oh, I'm receiving information from from within my body that's telling me, oh, your body temperature is too cold or something like that. And then I receive that information to my central nervous system, and I'm like, you know what I can do? I can put on a jacket, something along those lines. Or unconsciously, whatever, my cortisol levels are too high. I receive that information. My cortex, my central nervous system receives that information, and I say, let's reduce that amount of cortex. So again, this kind of continuous bidirectional feedback that's going on literally like every millisecond across all kinds of behaviors and unconscious processing of hormones, neurotransmitters, blood, the cell repair, etc. And this will lead us right into this idea called feedback looping. Feedback looping is a fundamental characteristic of information processing by the brain. At every stage of communication and processing, some of the fibers and connections loop back to the preceding stage to provide feedback that helps to control it. This enables the brain's motor control centers to correct and adjust their signals to the muscles right up to the moment these signals are sent. Feedback loops like these let us keep our balance while walking against sudden gusts of winds, for example. A complex task, such as playing a piano, involves highly complex connections because it requires the pianist to contract and relax many different muscles simultaneously, which are controlled by the cerebellum. So this is basically what I was describing before. We have this continuous process of updating information, communication, and processing that are occurring between different parts of the brain, different parts of your body at all times. And this allows for kind of like millisecond adjustments and how your brain is processing information and consequently behavior. So for example, we're walking and all of a sudden like a hurricane level wind hits us and we're like, oh, whoa, I got to brace myself. I'm adjusting in real time. So I'm basically, the central nervous system was originally telling your legs to move, walk forward, whatever, just kind of normal walking. All of a sudden a huge gust of wind comes and your body in real time is like, oh, this is your sensory receptors in your legs, for example, receive that information that, oh, wait, there's a big gust of wind, I could fall over, which then communicates to your central nervous system in real time. It's like, hey, stop doing what you're doing. Instead, brace yourself a little bit more, walk a little bit differently, stuff like that. So kind of the point is that these feedback loops are increasing or decreasing biological, chemical, and behavioral processes. So with that kind of large outline, let's get into some more specifics. There are two types of feedback loops. They are negative and positive. Negative feedback loops slow down a biological, chemical, or behavioral process. So negative, slow down, kind of straightforward here. So for example, when your body temperature rises, you may sweat to release heat. If too much heat escapes, you may end up feeling too cold, which will cause your muscles to shiver in an effort to make you warmer. And you can imagine this with hormones, for example. Think of something like cortisol, which is basically a stress hormone associated with full stress. So imagine you're just like super stressed out and there's a lot of like cortisol, I'm going to oversimplify this, in your body. And your body is going to say, oh, that is way too much damn cortisol, that AKA you are very stressed out right now. So here's what we're going to do. We're going to signal to parts of your body to stop producing cortisol, and thus slowing down that biological process, that chemical process of cortisol production. And behaviorally, that could tell you, well, you're super, like, on a biological level saying, hey, you're like really stressed out right now, maybe get out of this situation. So what you could do behaviorally is to leave that situation so you're less stressed out. But ultimately, what we're getting at here is that it's a negative feedback loop because your body, in the case of hormones, recognizes that there's too much of X hormone, aka cortisol. You're too stressed out, and what your body's going to say, that is too much cortisol. It's too damaging to your body. I'm going to send back neural signals or other hormones to decrease the production of cortisol. So you're kind of hitting that limit, and then you hit that limit of cortisol, and the negative feedback loop is again a signal for your central nervous system or other parts of the brain to stop producing cortisol. So thus slowing down that biological process. Versus positive, which speeds up a biological, chemical, or behavioral process. So for example, climate change is kind of a straightforward yet catastrophic positive feedback loop. So basically, as it gets hotter, for example, ice melts, shocking. And then that basically the function of that ice is to deflect heat back into the atmosphere. Broadly stated, we're being general here. The point of the ice is to reflect from a climate change perspective. The point of the ice is to deflect heat off the ice and then boom back out of the atmosphere, thus keeping our our temperature, our climate relatively mild. But as climate change increases, that ice melts, right? Now that that reflective ability is decreased because the ice is literally not there. Thus, instead, the ground, the new land that's exposed where the ice used to be, now cannot deflect that heat anymore, and thus that heat is trapped within our environment, thus heating up thus making the planet hotter, which then increases climate change, which then melts more ice, which then decreases the ability to deflect light or / heat back out of our atmosphere. So again, you can see this cycle basically is what we're getting at here of acceleration, of increasing that biological, chemical, or not in climate change, but behavioral processes. You can also see this during delivery when a pregnant woman is, or person is delivering a child. Basically, what's going on here is that as delivery gets closer, oxytocin increases, which increases the likelihood of delivery. So oxytocin is released during contractions, which then increases contractions, which then increases a child being born. So here we're speeding up. We have this combination of speeding up chemical, biological processes, and then ultimately delivering of the child. So again, that's kind of what the point being that we're increasing behavior versus negative. We're slowing down behavior, again, with our kind of cortisol example. So moving on to our next efferent division. Again, we already walked through the anatomic nervous system. Now we're going to walk through the somatic nervous system. Again, F, so sending signals from our central nervous system outward. So get the F out of here. All right, so somatic nervous system, organism's apparatus for responding to the external environment. It sends information to the brain from the body's various sensory detectors. The somatic nerves enable us to respond to the stimuli by moving through our environment, taking action, or speaking. One of the principal roles of the somatic nervous system is maintaining homeostasis in the external environment. So while the anatomic nervous system kind of deals with more internal, smooth muscles, glands, stuff like that, receiving information from your internal body to whatever, create more or release more hormones or something along those lines, decrease hormones, etc. The somatic nervous system deals with motor movement or voluntary release behavior. And primarily what we're interested in here is just kind of sensory neurons that are found in the somatic nervous system. So kind of like, again, fine-tuning those motor movements because our bodies are sensing whatever heats, coldness that we're about to fall over. So fine-tuning movements, receiving information from the external world, which then can be fed back eventually to our central nervous system to adjust our behaviors or as required. It's also associated with kind of just reflexes. So those like quick things that you're really not even thinking through. So again, kind of speaking to how this is involved in motor movement. So whenever you touch something, you pull back. You're not thinking like, oh, my hand is on fire right now. No, I'm going to pull my damn hand back before my skin catches on fire. So it's also involved kind of in those quick kind of unconscious reflexes as well. So those are just kind of the main kind of takeaways here. The sensory neurons and kind of those reflexes is sufficient. So as stated, the anatomic nervous system is involved in maintaining homeostasis in the internal environment by regulating vital organs such as digestion, respiration, blood circulation, excretion, and the secretion of hormones. The ANS is subdivided into two subsystems, the sympathetic, the SNS, and the parasympathetic systems. There are two branches of the ANS, generally work in opposite directions, enabling a continuous upward or downward control of the internal organs to maintain homeostasis in the internal environment. Quite a mouthful. But really what our big focus here on is really just kind of this regulation of organs and these biological processes that are occurring unconsciously. Like you're not thinking, oh, I need more blood. Let me produce some. This is happening on an unconscious level. And there's either increases in digestion, for example, or decreases in digestion for various reasons. But let's walk through some of these to make it a little more specific. Beginning with the sympathetic nervous system part of the ANS. When the organism faces a major stressor, the central nervous system goes into action and prepares the organism for physical or mental activity of fight or flight. The SNS is involved in dilating the bronchi and the pupils, accelerating heart rate and respiration, and increasing perspiration and blood pressure, but reduces digestive activity. Two neurotransmitters are primarily associated with this system, epinephrine and norepinephrine. So you can imagine a big bully is coming and they're gonna beat me up. And so my central nervous system is like, oh, that person is gonna beat me up. So at that moment, I'm like, all right, well, I gotta prepare to defend my honor. And at that point, then we're sending that get the F out. We're using our efferent division, and then specifically our ANS, and our division of ANS, the sympathetic nervous system, which is involved with fight or flight. And what's happening at a biological level, again, where you have a bully coming for us, and our SNS is like, all right, well, it's prepare for fight or flight, which means it's time to survive. So we're going to increase our heart rate, increase our perspiration, and decrease digestive activity to prepare for battle, basically. So you can see that we have kind of like this interactive effect between our central nervous system, recognizing that a bully's coming to get us, and then on this more unconscious level, the SNS, biologically preparing ourselves for fighting or running away from a bear, for example. Granted, if it's a brown bear, you got to play dead. Black bear, you got to fight them. White bear, polar bear, you're dead. So it really doesn't matter. Your SNS would be worthless at that point. So here, just know that the central nervous system is involved in fight or flight, and this is in response to, obviously, a major stressor or kind of a threat to us. Next part of the ANS is the parasympathetic nervous system, the PNS. It causes a general slowdown in the body's functions in order to conserve energy. The only things that the PNS augments are digestive functions and sexual activity. One neurotransmitter is primarily associated with this system, acetylcholine. So kind of the little catchphrase for this is that the PNS is involved with feeding or breeding. So for example, I have a delicious meal that's about to, that I'm like, oh man, I can't wait to have that whatever the new spicy chicken sandwich is. And how my body prepares to eat that food, the PNS says, all right, it's time to increase saliva, so then you can break down that food and properly digest it, for example. So just know that the PNS is associated with sexual behaviors, and digestive functions will be sufficient. All right, moving on to emotion, reward, punishment, and inhibition. There have been attempts made to identify nervous system activity components associated with different emotions. So basically just trying to measure some kind of correlation or between a particular set of nervous system activity and specific emotions. A review by Kreibig, we'll go with, concerning emotion in healthy individuals suggested some level of response specificity in the ANS to different emotions, with some overlaps. For example, anger was thought to be associated with this reciprocal sympathetic activation and increased respiratory activity, particularly faster breathing. So kind of during anger is what they're getting at. Our sympathetic activity, so increased activity in the sympathetic system. If you remember, sympathetic system, nervous system associated with fight or flight, so it kind of makes sense, you're angry. So an increase in sympathetic activation, increase in respiration activity, so I'm like sweating, I'm breathing hard, I'm ready for battle or running away, and faster breathing. So kind of the point here is trying to identify neural networks associated, or neural network activity, and kind of biological and chemical activation associated with particular emotions, to kind of attempt to identify the neurological underpinnings and biological basis of certain emotions, such as anger. Another approach has been to identify the brain areas and circuits responsible for reward and punishment processing. The main centers of the brain's reward circuit are located along the medial forebrain bundle. The MFB, just FYI, those kind of medial and all those kind of things are really kind of directions for where in the brain this particular network or region is. Turn it from rewarding to aversive stimuli. Fight or flight responses activate the brain's punishment networks. That is the periventricular system, or the PVS, which enables us to cope with unpleasant situations. These include the hypothalamus, the thalamus, and the central gray substance. So all we're doing here is kind of the same thing, trying to look for regions of the brain which are associated with particular behaviors, in this case here, reward and punishment, and identifying a particular network. That's kind of important to keep in mind, that rarely is only one part of the brain, or like this part of the brain does X, Y, Z, but rather more of this like network approach. So here we have this reward processing circuit / network thought to be involved with processing rewards and punishment. And then we have this example of like, oh, say we're in a good mood, but then something really bad. We're at a party, we're having a good time, then a fight breaks out or something like that. That fight activates the quote unquote the punishment network, the PVS, which helps us cope with this unpleasant situation or prepare for it. So again, kind of the biological process that underlie and are associated with particular reward and punishment processing and behaviors. So you don't need to know the medial frontal forebrain or PVS really much of anything on this slide, but just kind of the idea here is that researchers are attempting to identify parts of the brains associated with specific behaviors. Now, an interesting kind of system here is the behavioral inhibition system. The BIS is activated with both, is activated when both fight or flight seem impossible, and the only remaining option is to passively submit by doing nothing. The septo-hippocampal system, the amygdala and the basal nuclei, receive inputs from the prefrontal cortex. Long-term behavioral inhibition can be stressful with an increased probability of long-term illness. Large individual differences are observed in behavioral inhibition, which in adolescence can be associated with anxiety and depression. So we already talked about the fight or flight situation where we're preparing for a battle or we're going to run. Well, that's often in the real world, we don't live like in the jungle in general. So we're not typically running away from a bear and we can't just punch people. So for example, here you're listening to my lecture and you're like, dude, I hate this fucking guy. Like he is so annoying. Can he shut up? But you can't fight me and you can't flee it because theoretically you have to watch this to do relatively well in the class. So what you have to do is you have to inhibit that fight or flight. It's impossible to fight or flight from how annoying I am. So you have to inhibit that behaviorally. Now this is fine and this is what we kind of have to do. We all work like at times like shitty jobs, do something we don't want to do. However, long-term and like chronic inhibition is associated with increased probability of long-term illness because it's acting basically as a stressor that you cannot control as one possible theoretical reason. And kind of chronic use of this kind of theoretical system can be associated with like anxiety and depression because it's kind of straightforward. You cannot escape a very coercive, toxic, whatever environment, and thus kind of on a, or I should say, which was going to be associated with an increased level of depression or anxiety because it's like you can't escape it, you know. It's, so you're stuck in kind of this inhibition state, and you're kind of like in a state of like anxiety or chronic anxiety theoretically because you cannot fight or flight. You're kind of just like stuck there and you're worried about the next time, like, I don't know, I'll be mean to you or something, or your boss yells at you or something like that. So again, kind of that fight or flight, that unconscious process interacting with that central nervous system, our behavioral constraints interacting with each other in the real world, and consequently impacting likelihoods of developing a chronic illness. Moving on to neuroplasticity, learning, and memory. The hippocampus has been a focus for research on neuroplasticity. That is the nervous system's ability to change/adapt over time, and this customizes the brain. Neuroplasticity can be thought of as the brain's ability to change in form and function. The ability to potentiate transmission at the synapse by repeated stimulation, providing a neural foundation for learning and memory in terms of, quote, long-term potentiation, LTP. When we learn something, the efficiency of the hippocampal synapses increase, facilitating the passage of nerve impulses along a particular network. Much development in infancy and childhood is related to increasing/decreasing neural connections. All right, so kind of our big points here is this idea of neuroplasticity. This is critical to human development and health outcomes as well. So as when we were kind of first born, we are thought to be quote unquote very plastic. So you can think of like hot plastic, right? And many things shape our brain / that hot plastic, namely our environment. So what humans are really good at and is kind of adaptation. Adaptation doesn't mean good or bad. It just is. It's a biological, neurological, genetic process and behavioral process. And kind of the theoretical point of that is that humans in general are born kind of like worthless. So we all just like, you're born, you're like, you can't do anything. You're just crying and you can't move. You're kind of garbage. Unlike a baby like zebra or whatever. Like they're walking around pretty quickly. They can run around. They can grab some kind of food. Obviously, they're so close to their mother or father, whatever pack of zebras are called. But human babies they're doing nothing. Like it takes them a while to crawl, takes them a while to talk, not doing much. And kind of the idea here is that kind of that kind of lack of immediate readiness to interact with the environment is because we are very plastic. That is, it allows us, it allows the opportunity for our environment, that could be our parents, our families, our neighborhoods, our countries, our cultures, etc., to shape on a biological, neurological, and genetic level who we are. It literally customizes our brain. It shapes the form and function of our brains. And this is the kind of the biological and neurological process of why kind of the quote unquote the environment matters, or at least not why necessarily why it matters, but kind of the biological and neurological and genetic process underlining the evidence for how on the biological level that our environment shapes us, who we are. And that's what a lot of development is shaping those literally parts of your brain, the interconnection between different neurons, your genetic expression, which we'll talk about in the next chapter, becoming effectively products of our environment. And kind of long-term potentiation is kind of like this strengthening of these neural connections, strengthening these myelination. Myelination, again, matters because it allows for increased rapid communication between neurons, big, rapid, or vast networks of neurons that allow for complex thinking and action. So through time, as we perform the same action over and over again, we're increasing that myelination. We're increasing the connections between neurons involved in those particular behaviors. So you're playing guitar every day as a little kid, you're building up motor movements, cognitive processes that are associated with performance of that task, aka playing that guitar. And that's what we're kind of getting with long-term potentiation. You may have heard the Hebb rule before, that neurons that fire together, wire together, aka neurons that are active together, they build strength together. They get stronger, which allows for greater efficiency and communication between those neurons. There's kind of a misconception that's like, the more neurons, the better, or the bigger the brain, the better. Not really. What we're looking for is efficiency in the strength of connections between vast neurological networks. And actually, a big part of human development is literally killing certain neurons or certain connections and creating new neural connections, again, based on your experiences in the environment, which can be positive or obviously negative if you're living in a very adverse environment. Next, the endocrine system. Hormones act as, quote, messengers carried by the bloodstream to different cells in the body, which interpret these messages and act on them. In regulating the functions of organs in the body, the endocrine system maintains physiological homeostasis, such as cellular metabolism, reproduction, sexual development, sugar and mineral homeostasis, heart rate, and digestion are processes regulated by the endocrine system. Hormonal changes influence cognition. Sherwin, in 1997, suggested that estrogen helps to maintain verbal memory and enhances capacity for new learning in women, whereas other cognitive functions, for example, such as verbal memory, are seemingly unaffected by the steroid hormone. So a big important part here is hormones are carried by the bloodstream, all right? Unlike neurons activating like in the brain, communicating with each other through electrical and chemical signals. Now we have hormones being carried throughout the bloodstream to different cells in the body, with the goal of maintaining physiological homeostasis. And these hormonal changes that occur, a big increase during puberty, associated with obviously not just physical changes and sexual development, but also are correlated with particular cognitive processes. So these increased hormones increase the probability and success of performing complex tasks such as verbal memory, but also practicing verbal memory in return, almost like a positive feedback loop, also increases networks associated with brain networks associated with that verbal memory and hormones associated with, or the production of, or a greater production of hormones associated with verbal memory. So again, this positive feedback process underlying, in this case here, verbal memory. The main endocrine glands are the pituitary. You may have heard of the pituitary gland. And there's two of them, anterior and posterior lobes, the thyroid gland, the parathyroid gland, the adrenal gland, the pancreas, and the gonads. Endocrine gland releases hormones as a response to three kinds of stimuli. That is, hormones from other endocrine glands, chemical characteristics of the blood other than hormones, and neurostimulation. So we have our main kind of glands here. You don't have to like memorize all of these different glands or anything like that, because we're going to walk through a specific example. But hormones are released in response to hormones from other glands, so hormones interacting with each other, other chemicals in the blood, and neurostimulation. And we'll walk through examples of this in this chapter and then future chapters of how neurons influence endocrine production. Spoiler, stress is one. Cortisol will be an endocrine system or a hormone that we talk about. Building on that, the circadian clock. The endocrine system regulates the circadian rhythm and sleep/waking cycle with a variety of hormone releases. The secretion of some hormones increases during sleep, such as growth hormones, prolactin, and we'll go with luteinizing hormone. Secretion of other hormones is inhibited, such as the thyroid-stimulating hormone and cortisol. Some hormones are directly linked to a particular sleep stage. So growth hormone is typically secreted in the first few hours after the onset of sleep and generally occurs during slow wave sleep. So the endocrine system regulates the circadian rhythm. So how this plays out in real time is that certain hormones are released during certain parts of the day. So for example, or during the night. So during sleep, we release increases of growth hormones, which, you can think of a baby sleeping a lot and you're like, oh, you know the saying, you need to sleep a lot so you'll grow big or whatever. Well, there is a biological basis for this. In this case here, the secretion of growth hormone increasing while you're sleeping and making the babies big and strong or whatever, while a decrease in other types of hormones, such as thyroid stimulating hormones. And even more specifically, during certain parts of sleep, specific hormones are released. But for our purposes, just know that the endocrine system regulates the circadian rhythm and that kind of growth hormone that it increases during sleep. Continuing on with our circadian rhythm breakdown, cortisol is tied to the circadian rhythm and peaks in late afternoon, regardless of the person's sleep status or the darkness/light cycle. Research on effects of cortisol must account for time of measurement. Melatonin is released in the dark and is suppressed by light. Children near the equator typically have lower melatonin. That's because there's less suppression of kisspeptin. Artificial lights may impact/accelerate onset of puberty by increasing the levels of melatonin suppression. Thyroid hormone secretion occurs in the late evening. So as stated, associated with the circadian rhythm, particular hormones are released. Cortisol, this is kind of associated with stress, but it's not only stress. Cortisol plays very important roles in our body. For example, like growth is kind of associated with cortisol. But your cortisol levels peaks during the late afternoon. So kind of when you do cortisol studies, like measure like a stressor or something along those lines, you have to keep in mind what time it is that you're collecting data from the participant, because it's literally going to impact the levels of cortisol. So if you're like, oh man, person A is like has so much cortisol, it's crazy. And it's like, well, they're doing it at they're collecting data from participant 1 at noon. Right? And you're like, wow, that noon participant has way more cortisol than the person at 8 p.m. That 1 p.m. person must be super stressed. Maybe, but also we have to take into account and statistically control for the time of measurement of cortisol. And another hormone that we're talking about here is melatonin. You may have seen it in stores, you take it or whatever, and it's theoretically increases the likelihood of you sleeping. Be cautious with that. In many European states, you can't even buy it just from the store. You have to get a prescription. But regardless, melatonin increases as you get closer to the nighttime, thus increases in the likelihood that you fall asleep. And interestingly, again, you can see kind of impact of our environment, just like where you live, basically, aka how much sunlight you receive, with children near the equator typically having lower levels of melatonin. Again, an example of kind of our environment impacting these kind of biological processes. And interestingly enough, artificial lights, aka our phone, may impact/accelerate the onset of puberty by suppressing melatonin. So maybe these technologies increasing rates of puberty or earlier onset of puberty. Now, this is more an example, not to just overly read into that and say like, oh, the reason why, but it could be. There are research that suggests that they are correlated. So make sure that you know this kind of cortisol cycle, melatonin when it's released, or increased, I should say, rates of melatonin are released, and kind of this equator and artificial lights, aka phone situation. Diabetes is associated with the endocrine system's ability to produce insulin, which is affected by sleep. Sleep duration of less than 6 hours is a, quote, risky behavior for the development of chronic disease. Adults who report having 5 or fewer hours of sleep a night are 2.5 times more likely to have diabetes compared to people who sleep 7 to 8 hours per night. People who sleep 6 hours a night are 1.7 times more likely to have diabetes than their peers who sleep longer. People who sleep for 9 or more hours also have higher rates of diabetes. So one potential mechanism by which that sleeping and their circadian clock is associated with the risk of diabetes is through this insulin production during sleep. So thus, sleep is very, very important. It has to be a biological process, a reason, evolutionary speaking, for sleep. There are others, but this is just one here, and connecting to kind of our health outcomes. So in this case here, the increase of diabetes increasing for people sleeping, below 6 hours. So people, make sure you sleep or supplement it with some naps. So make sure you know kind of that risk factor associated with decreased or low levels of sleep, as defined as 6 or less hours. Now, this book actually doesn't do a great job with gender, sexual dimorphia, and identity, but kind of the idea here, just kind of broad strokes, the biological basis for gender identity is unknown, and if there even is one. Biological sex, however, is better understood. I'm not going to go that in-depth into this, because the next edition of this book will have a whole chapter dedicated to it, but I will include a previous lecture of mine, in Canvas, if you're interested on kind of gender and sexual dimorphism, which won't be quizzed on, but purely for learning purposes if you are interested in it. It's about an hour-long breakdown. Next, vitamin D. This is a steroid hormone, more specifically a sacchosteroid. Vitamin D normally arises in the skin from sunlight, or it can come from foods such as oily fish or from supplements. It's metabolized in the liver and the kidney. Vitamin D metabolites appear to be involved in a host of cellular processes, including calcium homeostasis, and cell differentiation. So we get a lot of our vitamin D from just being out in the sunlight. There's actually good research, we'll talk about later on, of people who live in Scotland, the UK. If you haven't heard, quite cloudy a lot of times, thus kind of decreasing levels of vitamin D, and kind of thus why when I'm in Scotland, I take daily vitamin D supplements to try and get that vitamin. And vitamin D matters because it's involved with all these kind of cellular processes, specifically cell differentiation is one, which basically just involves, you kind of have these undifferentiated cells, aka it's just kind of like a cell. You can think of it as like a free agent, not really it doesn't have a job yet. They're the unemployed cell. And then cells eventually get to be differentiated, aka assigned particular tasks. So with vitamin C, you can kind of boss them around a little bit and tell the cells, hey, you're in charge of X, Y, Z. But also, age-related decline in immune function is related to decreasing vitamin D levels in the elderly. Older adults are more likely to stay indoors and have lower activity levels. As a person ages, the skin produces less vitamin D. Vitamin D supplementation improves muscle strength and gait, especially in elderly patients. A reduced risk of falls has been attributed to vitamin D supplementation due to direct effects on muscle cells. Many authorities recommend vitamin D supplementation for frail patients. Vitamin D deficiency is a factor in a variety of illnesses. Pereira Santos in 2015 found that the prevalence of vitamin D deficiency was 35% higher in obese people and 24% higher in overweight people. So we have kind of this age-related effect wherein older adults are more likely to have decreased levels of vitamin D, and this can be due to a lot of variables, and this gets back to our interpretation. How do we interpret that finding? Well, one, behaviorally, older adults are more likely to stay indoors. They probably have lower levels of activity levels. Maybe they have less friends, people dying, or whatever, they're watching TV or something. So thus they're outside less, but also we have their skin producing less of vitamin D. So we have this combination, again, of biology and behavioral changes kind of contributing to decreases in vitamin D. This is especially hazardous to older adults because of the risk of falling, which is quite common. So vitamin D, lack of vitamin D can decrease muscle strength and thus increase the likelihood of falling. And then you fall, for example, and break your hip, for example. And then what happens? behaviorally, you're probably more likely to stay inside, less likely to get more vitamin D, and at the same time, the older adult producing less vitamin D as they age. So again, kind of this, kind of positive feedback loop, or just kind of mutual, multiple factors impacting this outcome. So rarely is it just like kind of one single thing. Or to make it a little more clear, rarely does a single factor / predictor explains completely a developmental outcome. One single thing does not cause a developmental outcome in general, overwhelming majority of the time, but rather it is a collection of factors that are involved in predicting any developmental outcome. Moving on to the microbiome. The new field of microbiome research studies the microbes within the gut and the effects of these microbes on the host's well-being. The gut is inhabited by 10 to the 13th to 10 to the 14th microorganisms, which is 10 times the number of cells in the human body and contains 150 times as many genes as our genome. The microbiota produce and secrete hormones, responds to host hormones, and regulate expression levels of host hormones. So stopping there for a second, that is just like a gigantic number. As we already talked about, the trillions of cells, trillions of neurons, that we fully don't have an understanding of how that impacts like complex behavior. Like we can understand like micro, a lot of the molecular kind of stuff, but how that ultimately translates into behavior is unclear. And also how our behaviors in return impact a lot of these microbes is also not entirely clear. However, we know that microbes influence metabolism, immunity, and behavior. Organisms within the gut play a role in the early programming and later responsivity of the stress system. Stress can induce an increased permeability of the gut, allowing bacteria and bacterial antigens to cross the epithelial barrier and activate the immune response, which in turn alters the composition of the microbiome and potentially increases HPA activity. Now, interesting, when I was at UF, there was another project going on that I had to work on that was looking at a mother's microbiome and how that was connected to birth outcomes of their newborn children, and theoretically in longitudinal studies trying to find an association or connection between mother's microbiome and their child's future behaviors. Now, one way that our behaviors or kind of our environments can impact our microbiome is through stress. So stress can theoretically increase permeability of the gut, aka bacteria, things that are maybe harmful to our microbiome, reaching kind of our gut by decreasing the barrier. Basically, there's this barrier. It's kind of like a blood-brain barrier, if you've ever heard of that. But here we have this barrier separating our gut biome that's native, whatever, quote unquote native to our cells, and then bacteria crossing that barrier and then beating up our microbiome and potentially damaging it or something along those lines. So in this case here, something stressful, maybe chronic stress, impacting our microbiome, which in return, that microbiome could feed back to our central nervous system or our endocrine parts of our endocrine system, aka our HPA activity, which we'll cover later on. But basically, the HPA activity, you don't need to know this right now, is one proposed neurological process by which cortisol is released. So we have here kind of a stress decreasing that the strength of that barrier, bacteria entering crossing that barrier, negatively impacting our microbiome, and then that increase that our microbiome that kind of providing feedback to our HPA activity or our HPA access, it's called, and then thus that HPA access then increasing cortisol production. So again, that's kind of like theoretical positive feedback. But ultimately, what we're concerned about here is that our microbiome is some way connected to behavior. Now, interestingly, if kind of damage to, quote unquote, damage to our microbiome impacts our kind of stress response system, that could thus kind of suggest that there is this programming effect, which you don't need to know now, we'll talk about in the next chapter, wherein our kind of stress response system is programmed through some combination of neurological activity, stressors we encounter in the real world, our ability to respond to those stressors, and our kind of microbiome kind of feedback to our central nervous system. There's increasing evidence links both hormones in the microbiome to the immune responses under both healthy conditions and autoimmune disease. There are many interconnections in the microbiome, and hormones may work through shared pathways to affect our immune response. So kind of as we said before with this HPA axis, again, you don't need to know that for this chapter. That is the hypothalamus, pituitary gland, adrenal axis. Again, you don't need to know that right now. But kind of the point here is that possibly our hormone pathways, our interconnections between our hormones and our central nervous system and our biome, our microbiome, may be communicating with each other through similar biological networks. Don't really need to know that, but that's kind of like the conceptual framework of this research. Now let's look at a specific study here. In a double-blind, placebo-controlled trial, participants were given a fruit bar that contained either the probiotic formula or a similar tasting placebo bar for 30 days. The experimental fruit bar group, that is, the people who received the probiotic formula bar, reported significantly lower levels of anxiety, anger, depression, and somatization on a number of self-report measures. They also had lower levels of cortisol in the fruit bar condition compared to the control group, aka participants who received the fruit bar with the probiotic formula demonstrated lower levels of cortisol as compared to the control group who just received a placebo bar. Now, again, kind of getting to that overinterpretation problem, we have the author stating that we have to cautiously conclude it is crucial not to oversimplify the idea that nutritional intervention in a healthy gut will be the panacea for profound psychological difficulties. Severe mood and paralyzing anxiety disorders are not going to be cured with probiotic yogurt or probiotic fiber alone. So this, you kind of get this a lot in kind of like marketing stuff like that. Like you go to the store and you're like, oh, take this, and then you're gonna feel way better. And it's just like food that is, and it says like microbiome food or something like that, which we again don't like fully understand. Like scientists don't fully understand what's going on, let alone like very specific microbiome. And it's important to keep in mind that just eating some food is just going to magically like cure you. Like we can't like go to some whatever. Like I can't go to my Kenyan student, my formerly Kenyan students, and be like, all right, just eat this microbiome bar, and boom, you're gonna be great. Everything's gonna be fine. So it's important not to just kind of rely on these kind of simple, kind of quick, easy selection, like kind of the solutions. Which is often kind of like marketed, obviously, because these people make products and they want to make money on it, which whatever makes sense. But as like scientists, you have to be cautious not to like proclaim certain things as kind of like panaceas, and instead kind of take a holistic approach that we've already talked about and be cautious, because just because one study finds something doesn't mean like, oh, that is fact or something like that. And therefore, everybody should do this new activity. But interesting research nonetheless, and trying to kind of unpack that kind of microbiome and how that impacts us, or how our lives, our environments impact our microbiome. Very interesting, regardless. Next, the immune system. The immune system is composed of two parts: the innate immune system and adaptive immune system. The innate immune system is made up of barriers and cells that keep harmful germs from entering the body. It includes our skin, our cough reflex, our mucous membranes, and stomach acid. If germs are able to pass through these physical barriers, they encounter a second line of innate defense composed of specialized cells that alert the body of the impending danger. So immune system, kind of straightforward here. We're trying to be healthy. We have two components we'll talk about. The innate immune system, again, kind of consisting of barriers and cells that keep harmful germs from entering the body. So our skin, basically. One function of our skin is like, okay, well, if I'm touching something very nasty and dirty that has bacteria in it, it's not going to get into like my bloodstream immediately, unless it's like corrosive, like acid or something like that. So that's why we wash our hands, because like, oh, it's on us, but it's not going to get into our body unless like we put our hands in our mouth or whatever, ears, nose, eyes, whatever, something along those lines. Or our cough reflex, like some kind of bacteria enters our, tries to enter our lung and we cough it out. That's kind of the idea here. We're trying to expel it from our body. Or stomach acid. So you eat something nasty and your stomach acid is supposed to like, kill certain bacteria. So you make sure you know what the innate immune system is. Next, we have the adaptive immune system. This is more complex than the innate immune system. It includes the thymus, the spleen, tonsils, bone marrow, circulatory system, and lymphatic system. That is, bone marrow produces white blood cells. These different parts of the body work together to produce, store, and transport specific types of cells and substances to combat health threats. Now, this is going to be more complex because this is going to be related to like T cells, for example, which we're going to talk about momentarily. But the idea here is that our immune system is learning in kind of real time. It's much more a dynamic process. Whether our skin is like, broadly stated, like not thinking, it's just like repelling, like it's just not allowing stuff to enter our bloodstream. While here, the spleen, the tonsils, our blood marrow, our blood cell, our white blood cells, they're learning new information. A disease enters our body for the first time, and we're like, oh, we know how to fight this. So let me learn about it, and then I can better like kind of fight it off next time. So this is kind of an adaptive, dynamic process, and that's why it's called the adaptive part of the immune system. Let's talk about the development of the immune system. Our innate system changes over the lifespan. Newborn babies have an immature immune system. The immunological competence is gained after birth, partly as a result of maturation factors present in breast milk, and partly as a result of exposure to antigens from food, environmental microorganisms. Early encounters with antigens help the development of tolerance, and a breakdown in immune education can lead to disease. At the end of the life cycle, older adults experience progressive deregulation of the immune system, leading to a decreased acquired immunity and a greater susceptibility to infection. Innate immunity appears to be less affected by aging than acquired immunity. So in general, babies, when they're born, they have a very active immune system, but they just like don't know what the hell's going on. They're like, oh, I don't know what to attack. I don't know what not to attack. They need to learn. They need to be kind of through that adaptive process, need to encounter things, and thus can learn from these encounters with these bacteria or whatever, these antigens, and then learn defenses. But also, breast milk is one process by which you can help a child mature their immune system, because mother's body obviously has experienced many diseases or illnesses throughout their life. So thus kind of like the classic, like, you want your kid to kind of interact with some antigens in food and the environment, because it allows them opportunities to kind of build or develop that immune system, that immune education, as it says here. Now, as we get older, our kind of our adaptive immune system kind of decreases in its efficacy. So that is kind of our acquired immunity, that immune education, that kind of the strength of that kind of decreases, and thus we have a greater susceptibility to infections. And this impacts more of that adaptive process, again, because it's more educational based, versus less impacted by like our innate immunity, again, our kind of stomach acid in our skin. Now, looking at specific cells, classically the T cells. These are types of white blood cells called lymphocytes. They attack infected or damaged cells directly or produce powerful chemicals that mobilize an army of other immune system substances in cells. Before a T cell is programmed to recognize a specific harmful germ, it is, quote, in a naive state. After a T cell is assigned to fight off a particular infection, it becomes a memory cell. These memory cells can remain in our system for decades. A healthy young person's body produces numerous T cells and is able to fight off infections and build a storehouse of memory T cells. However, with age, people produce fewer naive T cells, which makes them less able to combat new health threats. This also makes older people less responsive to vaccines, because vaccines generally require naive T cells produce a protective immune response. So again, we have these T cells who are kind of an army here, and they're fighting off against like illnesses or germs, something along those lines. And again, this is kind of a dynamic process where T cells kind of enter our world in a kind of a naive state. Then, however, they are assigned, they learn about an infection, they're decided to fight it off, and they become a memory cell. They've now been kind of programmed to fight whatever, chickenpox, I'm just making up something, chickenpox or something like that. Now, with age, however, we decrease the level of T cells that we make, and thus we're kind of less able to fight off health threats. Relatedly, this is kind of like one reason why vaccines traditionally, granted there's kind of new vaccines now, but vaccines traditionally are less effective for older adults, because they have kind of less T cells to kind of like learn, basically, very broadly stated, that the less T cells to learn and be assigned as memory cells as they interact with that vaccine. So the vaccine enters the system, the T cells are like, oh, I'm going to fight off that infection. Again, this has kind of changed now with with newer vaccines, but we're keeping it broad here conceptually. So basically lets T cells to kind of interact with that vaccine and learn from that vaccine, practice beating up the illness or whatever from that vaccine. And thus, older adults kind of need kind of higher rates of vaccination, or the vaccination is not as effective. So they have to come back and get vaccines kind of more frequently to kind of keep those memory cells, like in greater like shape and increase kind of the effectiveness of them. Now, it's just not T cells, but that's kind of what we're working with in this slide here. So just know that kind of age-related decline and kind of the differences between memory cells and naive cells. Inflammation occurs following infection or tissue damage when a rapid and complex series of reactions takes place to prevent tissue damage, isolate and destroy the infective organism, conserve and protect some micronutrients, and to activate the repair processes to restore normal function. Inflammation is a homeostatic process that is only intended to last a few days, but if it is continued indefinitely, is a risk factor for chronic conditions. Inflammation responses take precedence over normal body metabolism with the goal of restoring normality as quickly as possible. So the goal is to restore homeostasis basically as quickly as possible. So kind of the idea here is that we have some kind of damaged tissue or something like that. And the goal of inflammation is to isolate that tissue, repair it as much as possible, conserve what you can, and do so as quickly as possible so you can restore homeostasis, so kind of that stable state. So that's the primary goal. It's like something's wrong here, we're going to inflame this area, and then we're going to try and repair it. Now, you may have heard of like chronic inflammation. This is kind of a process where if inflammation is occurring for multiple days or chronically, years, whatever, this is associated with numerous chronic health conditions. And this can be related to a whole host of things, including like chronic like stress, living in like poverty or something along those lines, or like being in a very like abusive situation. Now, whether inflammation quote unquote leads to disease leads to inflammation, or whether both scenarios are true currently remains uncertain. Centenarians and other people who have grown old in relatively good health generally have less inflammation and more efficient recovery from infection and inflammation when compared to people who are unhealthy or have average health. Diseases of inflammation can result in autoimmune diseases, inflammatory diseases, and cancer. Immunodeficiency is when the immune system is less active than normal, and reoccurring and life-threatening infections can occur. Immunodeficiency can result from a genetic disease, acquired conditions such as an HIV infection, or the use of immunosuppressive medication. So kind of the idea is, and this is kind of a problem with direction, it's called a problem of directionality, aka does A cause B, does B cause C, is it some combination of both, is there a secret XYZ variable influencing both A and B? And this can be difficult to untangle. But we do have this evidence that older adults have less inflammation and recover more efficiently from infection. Is that some combination of just behaviors throughout their lifespan, diets, exercise, less stressful, having things called protective factors, which we'll talk about later, like high levels of social support, greater fulfillment, something like that, less stress or something, just, broadly speaking. We kind of know, we have evidence that those impacts rates of inflammation, but we have this idea as well that does inflammation like cause chronic disease, or does disease cause inflammation? And it's like probably this is called a bidirectional kind of process, probably like a mutually positive feedback loop, kind of mutually reinforcing, positive reinforcing process. But ultimately, disorders of the immune system can contribute to these autoimmune diseases and inflammatory. And this can be acquired through HIV, for example. So we have a behavior or some kind of genetic autoimmune disease, something like that. Now, briefly talking about autoimmunity, this results from a hyperactive immune system attacking normal tissues if they were foreign organisms. The common autoimmune diseases include Hashimoto's thyroiditis, rheumatoid arthritis, and diabetes type 1. Autoimmune diseases are chronic conditions with no known cure. Reductions of symptoms of autoimmune disease by a balanced and healthy diet, exercise, vitamin supplements, especially A and D, decreased stress, avoidance of any known triggers of flare-ups. So autoimmune disease is kind of like we have this immune system that's theoretically attacking intruders, germs, diseases, whatever. Now, however, instead of just doing that, your immune system is attacking everything. It's attacking your native normal tissues that are not infected with some kind of disease. Thus, your body is kind of like attacking itself. And depending on what it's attacking, these are associated with specific autoimmune diseases. And as stated, there are no known cures, but kind of the idea is that through certain combinations of medication and behavioral changes, such as exercise, diet, avoiding very stressful conditions, easier said than done if you're stuck in a context where you can't do so, that can decrease kind of the symptoms associated with particular autoimmune diseases. And kind of jumping back to sleep and rest a little bit, circling back around the circadian rhythm arguments or details. Sleep and rest are necessary for the proper functioning of the immune system. As stated, feedback loops involve cytokines in response to infection participants in the regulation of non-rapid eye movement sleep, that is non-REM sleep. Cytokines are chemical messengers involved in an anticipatory process for the preservation of body's homeostasis and defense. In sleep deprivation, active immunizations may have a diminished effect, resulting in lower antibody production and lower immune response than well-rested individuals. So our big takeaways here is that sleep and rest are critical for immune systems and a whole host of things as stated. And kind of what I want us to focus on here is kind of this diminished impact of immunizations. So people who are less rested may have lower rates of antibody production and lower immune responses, thus suggesting, again, sleep playing a critical role in kind of our antibody production and our immune responses. Sleep loss and disrupted sleep are strongly linked to acute and chronic inflammation. Chronic insufficient sleep is a risk factor in part because of an inflammatory state that results from sleep disruption. Circadian misalignment, that is adverse sleeping, eating, weak patterns, also induces inflammation, which has ramifications for shift workers. Late night shift work is a risk factor for inflammatory disease, including cancer and diabetes. In addition to the negative consequences of sleep deprivation, sleep and circadian systems have regulatory effects on immunological functions in both innate and adaptive immunity. So we have chronic insufficient sleep being associated with kind of chronic inflammation and even kind of like adverse sleep patterns. So for example, I want to highlight this late night shift worker is a risk factor for an inflammatory disease such as including cancer and diabetes. So someone who works from 8 p.m. to 5 a.m. or something like that, the overnight shift. So that kind of shift disrupting obviously your sleep patterns, your eating patterns, and really just how you experience the world being associated with increased risk for inflammatory disease. So it's important to kind of think through and interpret why late night shift work would be a risk factor for these onset of these diseases. Again, because shifting your circadian rhythm, aka staying up all night, shifting your wake patterns, because all of a sudden one day, then the next day you're back to a whole different, on a day off, I should say, you adjust your sleep pattern, and then like the day you go to work, you have to readjust your sleep pattern again. But also maybe late night shift workers are more likely to kind of have less social interaction. They're less likely to go outside and get vitamin D, because literally they have to sleep. And most people are up during the day, so they have less opportunity to hang out with people. So you have this complex situation where it's not just the circadian rhythm disruptions or misalignment, but also these kind of social factors. Now you're more isolated. Maybe you have more of a rocky marriage. You're probably, if you're working overnight shift in general, not always, but you're likely to be a little poorer. You need that extra money for working a late night shift. Again, a little more socially isolated, maybe a little more rocky marriage or partnership, something along those lines. A little more economic stress. Maybe you live in a more adverse neighborhood, something along those lines. All kind of possibly contributing to this increased risk of chronic inflammation and thus inflammatory diseases. So that's kind of an example of how you interpret that finding. Consumption of high fat and high sugar foods are associated with diseases such as diabetes and obesity, which can affect immune function. Moderate malnutrition, as well as certain specific trace minerals and nutrient deficiencies, also can compromise the immune response. So eating foods that maybe have left like nutrients in them, or having too much of just high sugar, not sugar naturally occurring in fruits, increasing the risk of diabetes. Kind of straightforward here. But again, this is probably going to be associated with race, class, disability status, because food deserts, or just having less money, or going back to that late night example, what's open at 3 a.m. during your lunch break? Well, I don't know. McDonald's is open, whatever's open, 7-Eleven, whatever the gas station is. Buc-ee's, we got that now in Florida. I think, yeah, a little bit Buc-ee's. Only that food being available. So you can see that kind of combination circling back to that late night shift worker, or kind of seeing how certain populations are going to be at greater risk of behaving, like whatever, negative health wise, but, constraint by their environmental circumstances. Undernutrition is associated with impairment of the immune function, can be due to insufficient intake of energy and macronutrients, and or due to deficiencies in specific micronutrients. Foods rich in certain fatty acids may foster a healthy immune system. Fetal undernourishment is especially risky as it increased risk of a lifelong impairment of the immune system. A variety of micronutrients have been implicated in improving the immune response, especially vitamin A, vitamin D, vitamin E, zinc, iron, and selenium. We're going to talk about that fetal undernourishment in our early development chapter. But for now, just understand that kind of eating those unhealthy foods or certain foods may negatively impact your immune system and increase the risk of diabetes, because, again, we're kind of insufficient intake of macronutrients that are critical for healthy development and maintaining our immune system and other important, and also neurological systems. And again, often people are engaging in kind of eating unhealthy because some combination of life constraints, maybe super stressed out, so kind of self-coping that way, or being, again, that late night worker, not having access to food, and then so that stress from that, and then you including kind of unhealthy food, again increasing the risk of inflammation or other mechanisms by which a decrease in immune system functioning would occur. All right, so let's get back to our final kind of main event here, and that is homeostasis. This refers to the principle by which the internal environment of the body is kept in a state of equilibrium by a multitude of fine adjustments at a hierarchy of levels, ranging from the molecular level to the level of the whole organism. There are 5 critical components that a regulatory system must contain in order to be counted as homeostasis. So again, what we're trying to do here is maintain some level of equilibrium. You can think of body temperature. If your body temperature is too high, you're at risk of death. You want to retain that classic human body temperature. And if you're too low, too high, you want to get back to that equilibrium. But it's not just body temperature. This is happening theoretically at a behavioral level and at a psychological level, as stated here. It can happen all the way molecular level, all the way to the organism as a whole. So let's walk through some of these more specific details about homeostasis. So physiologically speaking, for something to be homeostatic in nature, it must contain a sensor that measures the variable of the regulated variable. A value, measures the value of the regulated variable. My mistake. It must contain a mechanism for establishing the normal range of values for the regulated variable. It must contain a, quote, error detector that compares the signal being transmitted by the sensor, representing the actual value of the regulated variable, with a set point or range. The result of this comparison is an error signal that is interpreted by the controller. And we're going to power through this before we interpret it. And the controller interprets the error value or error signal and determines the value of the outputs of the effectors. And the effectors are those elements that determine the value of the regulated variable. All right, all straightforward, right? I don't need to explain that, so right there. But no, so basically what we're getting at here, without getting into like these super specifics here, is that we have that normal range that we talked about. So we have in the previous chapter, and we have this range of physiological processes. Again, blood pressure, hormones, the neurotransmitters, whatever. We have a range of which the values of that variable, that neurotransmitter, that cell, that blood pressure, that hormone should be. All right. So we're constantly measuring our body this regulatory system is constantly making sure that or checking for that whatever XYZ hormone neurotransmitter is within that normal range. So they have to be able to kind of check that out, and it has to be able to detect error. Detector is kind of measuring where that hormone actually is, and trying to determine if that hormone is outside of that set point range or set point. What the goal being, if you're too high in cortisol, too low in cortisol, to increase or decrease production of that hormone to get you back to that homeostasis, back to that normal range, your set point of cortisol, for example. So this is what I want you to take away, that broader kind of construct. If we want kind of that equilibrium established, we want monitoring of the hormone, the neurotransmitter, whatever it is in our body, and that regulatory system has to be able to adjust the production or decrease in the production of a particular hormone to maintain homeostasis. That's what we're looking for, the kind of conceptual overview of that. Now let's take those principles of physiological homeostasis and apply it to our construct, psychological homeostasis. It's best explained in two stages, starting with the classic versions of physiology, followed by the new version extended to psychology. All people are oriented towards seeking and or preserving physical and subjective well-being at a set point that is kept at the highest possible level. We tend to approach new resources in the hope of finding a reward for this behavior, and equally to avoid punishing or confrontational situations, this theory argues. If we do encounter a threat, our behavioral options include either fight or flight, or inhibiting our behavior so as to go unnoticed and to avoid confrontation. So kind of our bedrock principles right now is that we are trying, we enter the world, we explore the world, trying to preserve our well-being, our physical and subjective well-being at the highest possible set point as possible, all right? So we're looking for rewards, and that doesn't mean just oh, I get a candy bar, but this could be fulfillment, whatever, meaning, whatever, purpose, collective action, whatever it is. And kind of try and decrease and try and avoid punishing in confrontational situations. So in general, you don't want to just get punched in the face or stabbed or something, or get fired from your job, whatever it is. However, we do encounter threats. And as we talked about, we have this physiological system, this fight or flight, okay? So we can punch someone in the face. So oh, someone's going to fight me, or my boss is being mean to me. I'm going to punch him in the face, or I'll just leave the job, which I almost did when I worked at Panera, just walk off in the middle of the shift, which is possible. But also, we can inhibit our behavior. So we can inhibit this fight or flight process and just hide it. So a person doesn't know that we're pissed off, and an attempt to avoid confrontation. So we're attempting to keep our set point, our subjective well-being and physical well-being as high as possible. We're looking for rewards, but we're going to encounter threats, and we can either punch, we can run away, or we can inhibit to hide how we are feeling and avoid confrontation. That avoidance or that hiding, going unnoticed, is an adaptive value in behavioral inhibition. Adaptation does not necessarily mean positive. I'm kind of now granted, some people would argue others, but I'm from a lab and kind of theoretical background. Adaptation does not mean positive. It just is. It's a neurological, biological, genetic and behavioral process wherein you adapt to your environment. Now that environment could be bad. The environment could be whatever positive. Again, being overly broad here. So it's not necessarily that the adaptation is bad itself. Is one way that you can think about it. But the environment itself is negative. Now, of course, our adaptation behaviors can be negative. Whatever, we can drink ourselves to death, etc. But at the root of it is not necessarily that adaptation, but that adverse environment, and which we can maybe recognize and then change our adapt in a different way, but kind of a different perspective here. But ultimately, though, there is an adaptive value in behavioral inhibition, biologically and behavioral speaking. For example, a mouse scurrying through the grass suddenly notices a buzzard flying overhead. Out of fear, the mouse freezes, thus avoiding attracting the buzzard's attention. Playing dead until a predator has passed can be beneficial as long as the tension of waiting does not have to go on for too long. So in this case here, we're a little mouse. We are see that we're about to be eaten. So what do? We can freeze and try and hide, try and go unnoticed. So that's our behavioral, we're trying to not be noticed by the buzzard, or we can just play dead. But while we're doing that, we are at extreme tension, right? Because we're nervous. It's a life and death situation. We're very, very, very stressed out. So yes, we can, but that's required because we live. However, if you're stuck there for days, months, years in an adverse situation like that, that can have negative impacts on your health. So let's apply that to a real world example. And by real world, the mouse is the real world, but a human example. Imagine you aren't a mouse and instead are a worker and you're working for an exploitive boss. The worker cannot flee or fight, or they would be out of a job. So you can go to HR, you can punch your boss and probably go to jail, you can join some union, or you can just eat it and suffer. This do-nothing strategy ultimately can have disastrous effects on their health. Chronic inhibition can increase blood levels of glucocorticoids, which harms immune system functioning. This weakening of the immune system is theoretically why remaining in a prolonged state of behavioral inhibition can cause all sorts or associated with all kinds of health problems. So again, we have this homeostasis. We want to be at the highest subjective well-being that we can, and then when we encounter a stressor, we can fight or flee, physiologically speaking. We prepare, we dilate, we raise our respiratory, we are decreasing our digestion and the behavior. We're going to fight or we're going to flee, but also, as stated, you can inhibit. And in this case here, imagine that you're a worker and whatever, you're a single mom or something, and single mom who works 2 jobs. No, we love it. And your boss sucks. Maybe they're like harassing you, or it's just like an asshole to you. All right, so you're pissed off, and you're like, okay, I can punch my boss in the face, I can run away, but I can't do that. If I punch him, I'm probably gonna go to jail / fired. If I flee, aka just walk off, I'm gonna get fired, and now I'm screwed. I have no money. I'm a single mom. What can I do? I have no option. Okay, so I can either do something like about it, change my environment theoretically, change the workplace, go to HR and be like, oh, my boss is a naughty boy and I want a new boss. Or you can be like, woo, we're going to overthrow this boss or something. I don't know, join a union or something, empower yourself, something along those lines. Again, ultimately, the point, though, is that you're changing that environment. Or you just have to eat it, aka you do nothing. Now you're doing nothing and say you have to work there for years. Now you're in that prolonged state of tension, that prolonged state of fight or flight kind of for hours per day, and also probably not making that much money. And you also have stressors at home also contributing to it. So you can see that kind of cumulative effect here. But ultimately, on a biological level, that chronic inhibition can increase blood levels of glucocorticoids, which are broadly stated just cortisol. They're stress hormones, which again can negatively impact immune functioning. Thus, again, one biological process by which that state of inhibition can negatively impact health outcomes, because we are not able to maintain homeostasis. Instead, we have to kind of like suppress it and be like, okay, well, I can't have that theoretical set point that I want of subjective well-being. Instead, I can never hit there. I just have to suppress it and be at like a lower level of subjective and physical well-being, which again is associated with a higher likelihood of acute and chronic health problems. Now, one source of inhibition can also be our imagination, our fear of failure. This can lead us to foresee so many potential negative scenarios that we end up doing nothing. To do nothing and maintain a dream may be a better option than to act and to fall flat on one's face. Whichever way one looks at the issue of inhibition, it has an obvious connection with homeostasis, a striving towards equilibrium. Now, one source of inhibition, as stated, can be imagination. Now, inhibition, again, does not necessarily have to be completely negative or something along those lines. So again, you cannot punch, well, maybe you can, but it might be worth it, I don't know. But in general, there's going to be some kind of repercussion for punching your boss in the face, even if they're being a jerk to you. Or you can imagine some like a 1920s like colonized population or whatever. It's like, okay, well, I'm kind of inhibiting like overthrowing this colonial regime because, hey man, this is a big risk. I can literally die, and a bunch of people can literally die. So it's like, well, maybe it's better right now to do nothing and maintain that dream because it's so risky that we're going to fail. And that's not necessarily, no like value judgment on it or whatever. It is just kind of like a calculation that you're trying to do in your head about what the likelihood of success and failure is. But ultimately, kind of the point you can see here is that in the real world, this kind of this homeostasis, this equilibrium being met or not met in very adverse conditions, again, exploitive boss or whatever, colonized population or something along those lines, that increasing that chronic tension, that chronic inhibition, increasing the likelihood of chronic physical and mental health disorders or diseases. And we'll wrap it up with the schematic here. You really don't need to know this kind of like schematic thing, but this is kind of what it looks like here. This combination of physiological processes, neurological processes, and behaviors. And those behaviors, again, can range from like, oh, I got to go to work today, or I got to get out of bed today, or I got to listen to this idiot talk about whatever, fight or flight for an hour and a half, or whatever, something more extreme like, oh, I'm like a super oppressed population. But you can see that kind of theoretical connection between physiological homeostasis and behavioral homeostasis, fight or flight, and inhibition. All right, I think we can wrap it up there. So thank you so much, everyone, for listening, and I hope you have a great week. Bye.